Hello all. The title of our talk is sOfT7, Revealing the Secrets of the Siemens S7 PLCs. This is joint work with Professor Eli Biam and three of our students, Maxim Barsky, Idan Raz, and Alon Dankner, who is here with me. We are all from the Faculty of Computer Science in the Technion Israel Institute of Technology. My name is Sarah Batan. I'm the founder and CEO of Cyclock that provides secure system design and audit services. I'm also a senior researcher at the Technion Hiroshi Fujiwara Cybersecurity Research Center.
My name is Alon Dankner. I'm a security researcher and a Technion graduate.
Siemens S7 PLCs are certainly the most researched and attacked ones. The reason is twofold: ubiquitous deployment in critical facilities, and the vendor, Siemens, set a high security standard. In fact, it was the first ICS vendor to integrate cryptographic protections on its PLCs. So here's a quick history of malicious code execution on Siemens S7 PLCs. The first to do it was the infamous Stuxnet worm discovered in 2010. It exploited a vulnerability in Siemens Windows software to inject a rogue control program to the PLC and tamper with the HMI outputs. This was before Siemens security enhancement and was actually a trigger to it. In ROG 7, the work we presented here in 2019, we came up with the ROG engineering station Python script that exploited vulnerabilities in the S7 protocol to perform stealth injection of an unauthorized control program to an S7 1500. We also find out that all the PLC from the same model and firmware version use the same key pair. In the same year, at Black Hat London, Abbasi and his team exploited a vulnerability in the S7 1200 bootloader and demonstrated arbitrary code execution. They were also the first to find out that the S7 PLCs are using the Adonis kernel. In 2021, Tal Keren from Clarity exploited a vulnerability in Siemens memory management to escape the control program sandbox and got remote code arbitrary code execution in the Adonis kernel. Our current work takes the capability to run native code on the PLC and create a ROG PLC a few steps forward. Remember the Purdue model, where the PLC communication is restricted only to the planned local HMI and engineering station? Well, you can start forgetting it. Industry 4.0 and the digital transformation are changing the ICS architecture model. New architectures are emerging where the PLC communicates through a service bus that might reside in the internet with other ICS components, part of which might also be scattered in the internet. So smart manufacturing brings forward new PLC requirements. They're required to run integrated development environment. They're required to support new communication protocol and even perform extensive cloud communication. Hence, the vendor must be agile and flexible, yet they must preserve existing IP and technology and cannot start from scratch. So the solution the vendors came up with are the software PLC. This is a PLC that contains a VM that runs a general purpose OS. Mostly we've seen Windows, but some are running Linux. Now, the fact that the standard OS is running on the PLC CPU leads to the usage of a standard CPU. Another VM runs the PLC code, which usually runs on the vendor's proprietary operating system. As we have two operating system running on the same CPU, the general purpose and the proprietary, and they're running in virtualized sandboxes, and the virtualization is implemented by a hypervisor or VMM. In Siemens' case, the CPU the PLC is using is an Intel Atom, a multi-core, where a Windows embedded OS is using 3 of the cores, and the 4th core is used by Siemens' proprietary operating system, which runs the PLC. Siemens ET200SP Open Controller is Siemens' version of the software PLC. It is a software version of the S7 1500. It was introduced to the market at 2015. Now, virtualization brings with it significant operational advantages. For example, you can update the Windows, and when it is restarted, or even when Windows receives a blue screen of death, the PLC continues to run without interruption, since it runs on a separate VM. Siemens have also used virtualization to prefer separation of communication and to decrease the attack surface of the PLC code. In the new architecture, the PLC communicates only with the field devices. All the communication with the upper layers of the Purdue model that contains the AGMI and the engineering station and might also reside in the cloud is performed by the Windows VM. The device that we tested is CPU 1515SP. Now, let me take you backward to about 6 years ago, before we started our ROG7 research. Our first intention, original intention, was to attempt a vulnerability search on the S7 1500 firmware. At that stage, we found out that it was encrypted, and we couldn't extract the plaintext firmware from the PLC. So we fell back to protocol reverse engineering, and the result was our ROG7 research. When we learned about the new software PLC and the new architecture, we thought, okay, let's give it another shot. And thus we started our quest towards the Siemens PLC plaintext firmware. Now, when the PLC boots, it immediately enters the Windows VM, a jailed environment, and all we can see is the Windows screen. So our first attempt was to run a different operating system on the PLC hardware. So we brought our own disk on key that contained Ubuntu, and we tried to run it on the PLC. And surprise, we successfully ran Ubuntu on the PLC hardware. Through the Ubuntu, we found that there are 5 partitions in the PLC internal memory. We found that SDA1 contains the Windows file system and also the GRUB files and the hypervisor binaries. And there are other 4 partitions in the internal memory, for example, that contain some other stuff. For example, SDA5 contains the Siemens project file. By analyzing the GRUB files, we found that the hypervisor is running in 2 stages. At the first stage, the hypervisor configured the PLC hardware. At the second stage, it loads 2 virtual machines. The first virtual machine contains Windows, and the second virtual machine is loaded from a CPU.elf file that contains the mysterious SWCPU in an encrypted form. Hence, we gather that the PLC software architecture is a VMM and hypervisors that runs on top of the hardware, and it runs 2 VM. One VM runs the Windows embedded operating system, and the second VM runs this mysterious software CPU. From our analysis of the GRUB configuration file, we also figured out the CPU load sequence, the open controller boot sequence. So after the BIOS is running, a GRUB bootloader is running that runs the first stage of the hypervisor, configures the hardware, the second stage of the hypervisor that loads the 2VM, the embedded Windows that communicates with the HMI engineering station and optionally with cloud platform, and the software CPU that communicates with the field devices. Surprisingly, at this stage, we found out that the VMM binaries, the GRUB configuration, and the CPU.elf files are also accessible from Windows. The implication is that an administrator that has read-write privileges, of course, on all the file system, can read those files and can even write and his own software, the software PLC files, or encrypted software PLC files, or change the GRUB and the hypervisor binaries. Now that we had access to the hypervisor's binaries, we searched for the part in the hypervisor that loads the plain text binary of the PLC to memory. So we did it by reverse engineering the hypervisor binary, specifically the second stage of the hypervisor. Now, looking at the binaries, we found out that the hypervisor is looking for a specific magic at the beginning of the encrypted software CPU file, which is the S3 magic. Now, we tampered with this magic and got an error message that said that the PLC failed to load its firmware. Looking at the binaries, we found this error message, and before it, we found the code to the decryption function. So we now have the part in the code that calls the decryption function that decrypts the PLC firmware in memory. Now, once we got to the decryption function, we started to try and reverse engineering and understand what the decryption function is performing, but we found that the code is very sophisticated. And we understood that static code analysis is not enough to reverse the decryption. We needed a dynamic code analysis, namely we needed a debugger. Now consider that the PLC is running in a hardened, restricted environment. Siemens removed some of the functionality from the hypervisor. So we could not install our own debugger in the PLC hardened environment. So we came up with our own primitive yet very effective debugger. We found out that int3 is connected to the CPU debug interrupt handler, and this handler creates a dump of all the registers and the memory. So we simply inserted int3 to places in the code where we wanted to break and examine the content of the registers and the memory. Using our int3 debugger, we found the runtime call to the decryption function, its argument, and the local variable it allocates on stack. The arguments in the local variable includes pointer to the ciphertext and the clear text of the CPU elf, and we could see the content of the memory pointed by those pointers in memory. So this was a very frustrating stage in the research for us. We had the plain text of the firmware in memory, but we could not export it from the PLC to analyze it. It's like we found ourselves in front of a locked vault in a secure room with CCTVs and motion detectors all over the place, and all we had is a tiny screwdriver, namely our int3 debugger. We knew that with enough effort and time, we could lock the vault in the standard common way. But we decided to think out of the box, go completely nuts, and who knows, we might get lucky and it will simply work, or even turn out to be much easier. So here's what we done. Excuse me for a moment. Okay. Okay, taking our frustration to innovation.
Ready?
I'm ready.
Okay, we successfully moved the vault from the PLC restricted environment to our own powerful attack environment, which is based on Linux. But the vault is still locked. So I give you Alon as the rock.
Thank you, Sarah. So, our idea was to run the VMM or parts of it in an environment that is easier to debug, that allows us to produce output, and mainly that allows us to export the plain text binary from the VMM. We just couldn't do it directly on the PLC itself. Now, the VMM is an x86 binary, so it may seem straightforward to run it, but there are several challenges that must be addressed. First, the VMM runs in hypervisor mode, and we wanted to run it in user mode. Second, the VMM has its own kernel and libraries, while a standard Linux has libc. To address these challenges, we use dynamic binary instrumentation. We used it to start the execution of the VMM from a specific location, to add our code wherever we wanted, and replace VMM functions with our own function. We chose Intel Pin as our binary instrumentation tool. It is typically used for performance analysis and architectural studies, but we used it for our purposes. That is, to unlock the vault. When our decryptor starts to run, it loads the binary of the VMM to the memory and replaces VMM functions with libc functions using hooking. We placed another hook inside what we identified as the decryption loop. The decryption loop takes a block of ciphertext, decrypts and decompresses it, and we added a call for a function that exports the plaintext to a file. Intel Pin starts running the VMM from the VMM entry point, but we don't want to run the initialization or the first stages of the VMM. We want to go directly to the decryption. Therefore, on the first instruction, we use a hook to hijack the control from the VMM and transfer it to our decryptor. But before we jump to the decryption entry point, we need to prepare the environment. To work correctly, the function must receive the correct set of arguments. The second argument, RSI, is a pointer to the encrypted software CPU. RCX points to a buffer that is used for the plaintext. Now, we also point RSP to the beginning of a large buffer we created. And this is interesting because the VMM actually uses this buffer as a stack. After we prepare the environment, we redirect the control straight to the decryption entry point. At some point of the execution, we may encounter a call for a VMM function, like vmmalloc. Instead of jumping to the original function, we use the hook we placed earlier to jump to malloc. Eventually, the VMM reaches the decryption loop that decrypts and decompresses the software CPU block by block. For each block, we call the writeElf function that writes the buffer that contains the plaintext to a new file. So with any iteration of the decryption loop, we write another plaintext block to the file, and this is how we build the decrypted software CPU. At the end of the decryption loop, we actually get a legal ELF file, and you can see some of the ELF segments in the slide. Now, let's see a demo of our decryptor. The VMM directory contains the binary of the VMM and the encrypted software CPU. We show here the MD5 hash of the software CPU, which is equal to the one on the PLC. As you can see, the software CPU is encrypted, and it begins with the S3 magic. Make run starts the decryptor that runs the VMM with our modifications, and the output comes from the decryption loop. At the end, we get a segmentation fault, but we just don't care because we ran the VMM long enough to get the plaintext. The decrypted software CPU is delivered in output.bin. As you can see, it begins with the ELF magic, and readelf shows that we actually managed to parse it. Now, check this out. We've just run a PLC binary on an Ubuntu machine, which doesn't even sound possible, and still we got the decrypted software CPU. Therefore, it is crystal clear that the decryption key is hard-coded. Now, back to you, Sarah, for the rest of the talk.
Thank you, Alon. So our quest ended. The key was the firmware last line of defense. And since it was literally glued to the vault when we opened it, when we took it, we opened it and exposed the firmware. Thus, we got the plaintext firmware. Initial analysis of the software showed that it contained much more from what is required to operate the software CPU in ET200SP. In addition to the PLC software, it contained full libc implementation, OpenSSL library, and even binary encoded in MIPS ISA. Moreover, it contains strings that we were familiar with from previous research, from unrelated parts of other hardware-based S7 PLC. So the good intention of reducing the PLC attacks survey failed because we found out that a huge code base is carried from previous models of the S7 PLCs into this software PLC, hence the attack surface is indeed increased and not decreased. Now note, although it's a different model, it's a software PLC, 99% of the ET200SP code is shared with the rest of the S7 1500 PLCs, including the hardware-based PLC. Now, what could Siemens have done to prevent us from successfully decrypting the firmware? If they would have separated the key from the VMM binaries, we would not have been able to use Intel PIN to decrypt the software CPU. If they would have used secure boot, we would not have been able to implement our Int3 debugger. If they would have encrypted the hypervisor binaries, we would not have been able to reverse engineer them. And again, if they would have implemented secure boot, we would not have been able to run another operating system, namely Ubuntu, under PLC hardware. But Siemens didn't deploy any of these preventive measures in the ET200SP. Secure boot is not implemented, the Intel Atom TPM is not used, and the VMM binaries are not encrypted. To summarize, these are the basic mitigation that we would like to see in a secure PLC. The key must be separated from the code, preferably stored in a hardware module, for example, TPM. Secure boot must be implemented to prevent system manipulation. The file system must be encrypted to prevent static code analysis. But as I said, none of these mitigation were implemented in a ET200SP. Siemens confirmed our finding, and they were interested in possible customer impact. The truth is the customer impact of this attack is severe. The PLC firmware leakage exposes the full SIMATIC S7 product line since we found out that the code base is shared. So via exploitation of non-vulnerabilities, the hardware-based PLC can be attacked. And the horses may have already left the stable. A recent finding, which is not part of this research and is part of a different publication, we found out that an attacker who gains admin rights on the Windows VM can replace the PLC firmware with its own crafted rogue PLC firmware. And this means that an attacker that gains control over the Windows VM, which has a huge attack surface since it communicates with the upper layers and maybe with the cloud, can run his own GRUB PLC firmware. We shared the full details with Siemens before the talk. Now to summarize, as of 2019, Siemens had a 31% of the PLC market share. Those PLCs are deployed in critical places like power plants, water facilities, transportation system, and even nuclear reactors. The firmware leakage exposes the full S7 SIMATIC product line to known unpatched vulnerability. And this is a design flaw. There's no easy solution. It's not like Siemens will distribute a patch and it is immediately fixed. The solution is operationally much more sophisticated. I would like to use this opportunity and this stage to send two messages. The first message is to the community. We suspect that Siemens is not the only ICS vendors that has problems securing this new PLC architecture. We didn't check other vendors, but the reason to our suspicion is that secure binding to hardware and large-scale key management are tough operational problems. So I challenge you all, academies, standard bodies, security and ICS vendors, to look for a solution to this problem. This is especially important now since ICS architecture are currently shifting from walled garden to open, cloud-oriented environments. Another message I want to send from this stage is to the ICS customers of all ICS vendors. I'm addressing you. You're the asset owners. You will suffer from the impact. As long as you will not make clear specific requirements, you will continue to get security mechanisms that the vendor chooses to implement, which are not necessarily the ones that you need. I thank you all for your time and your attention.